So we start. Before we go to chapter 5, just quickly go back to still need to do one more graph. Today so find the amplitude period, phase shift and vertical shift. And then sketch. So just do find one by one. Amplitude is going to be the absolute values of the number in front of cosine or sine. So absolute values of 3 or just 3. Period. For sine, cosine typically is a 2 pi. However, we have the coefficient of x, so we're going to divide by that. Divide by pi. Whatever coefficient of x. By the way, if this is negative pi, we're just going to take the positive. Yeah, just take whatever the coefficient article with x and positive. If it has negative, just going to put pi in here. And pi and pi cancel out is 2. So the period is 2. Phase shift. Phase shift is where we let in the argument or the angle of the trigonometric function equal to 0. I'm going to add pi on both sides. Pi x equal to pi. And then divide by pi. So x is equal to 1. That is the phase shift. Vertical shift. Vertical shift is whatever the numbers here. That is added to the trig function. So it's negative 1. Right. So that's all we have. And now we put together onto a graph. So first, what do we have first? On the x-axis, we're going to need to use this two, the period and the phase shift. So we're going to start at x equal to 1, and then the period is 2. Now, let's say we have something to worry about. For example, if we start with 1 about this much, if this is 1, then the period is going to be 2. Will be twice as much, so about this much. In that case, the graph kind of small in terms of a period. So in that case, if we're going to sketch it and look reasonably, we choose the phase shift a little bit bigger. If it is the case, then the period 2 will be twice as long, and that look more reasonable to graph. We want the period to be a little long, so we can have the graph is easier to graph. So we start at 1. 1 period is 2, so we have 2, and then we also can go back from 1 back to -1. And so we can do that. So where start a period, where start is the phase shift, the period is from that we go 2, which is twice the phase shift where we start. Alright, now next, the vertical shift is where the graph start. So that is the middle line. And we have the middle line at -1. And then the amplitude is 3, meaning from this center line or the middle line, we go 3 up and 3 down. So 3 up from -1, 0, 1, and 2. So there will be 2 on the top. And -1, -2, -3, and -4. So go from -4 to -2, out from -4 to 2. Now, we know we start the phase shift at 1. And go, we start 1 and go on 1 period of 2. So this is 1 period. And we start 1. Right. And then finally, this is the graph of cosine. So the pattern for cosine is maximum, middle, minimum, middle, and then max. So maximum, middle, minimum, middle, max. So that's for 1 period, and then we just copy and paste this throughout the whole interval. So pretty much that. So we need this for information to sketch the graph. Before we go to the next chapter, I just want to bring this up real quick. Let's say we have this function. Now, suppose that I also ask you to graph suppose instead of sketching that function over there, suppose we try to, instead of sketch that function, we sketch 3 secant pi x minus pi minus 1. So pretty much the only thing change from that function to this function is that we go from cosine to secant. But notice that secant is the reciprocal of cosine. So all we do will be exactly just this. Everything, the graph we're going to sketch the same thing, but the graph of the cosecant is going to be different. The only thing different is when it is equal to 0, there's the vertical asymptote. So the graph of the reciprocal function, we're going to graph sine cosine first and then go to the reciprocal function. When there is the middle line, that was equal to 0, and the graph will bounce. And then so on, right? So whenever the graph cuts the middle line, that's the vertical asymptotes, and then the graph will bouncing from the maximum and the minimum. So that's where we go from a graph of a function from sine cosine to a reciprocal function. So just want to bring that up. Now with that we go to the next chapter. Verifying identities. So before we go to the next section, before we actually prove anything or verify anything, we need to go over all the identities we have up to this point. the reciprocal identities. By the way, hope you still have all the quick reference code that we have from the beginning, right? One of those is the hexagon trig. So again, tangent on the top, cotangent at the bottom, and then sine, cosine, secant, cosecant, right? Opposite from one are reciprocal functions. So tangent is reciprocal cotangent, sine reciprocal cosine. Sine reciprocal cosecant, and secant is reciprocal cosine, and so on. So that hexagon thing, just going to put that here. Just write out all of those now. So sine is 1 over cosecant, cosine 1 over secant, tangent 1 over cotangent. Alright, now this will be cosecant. I don't know why. What doesn't work? Right, and then cosecant. Of course, reciprocal sine, secant, reciprocal cosine, and cotangent, reciprocal tangent. Right. Next, the quotient identity. Now this is a lot more than just what we have on that side. Tangent is sine over cosine. And cotangent cosine over sine. Of course, in the hexagon, when we have whatever the function on the top, so tangent is equal to sine over cosine, secant over cosecant, right? And then of course 1 over cotangent. So whatever the function on the top, we will have 3 ratio. So secant is cosecant over cotangent, tangent over sine, or 1 over cosine. Yeah. So the quotient identity and reciprocal identities, we can get from the hexagon easily. C. Pythagorean theorem. The Pythagorean identities. Cosine square plus sine square is 1. So on here, cosine square plus sine square is 1. 1 square plus tangent square, secant square, and cotangent square plus 1 is cosecant square. By the way, I think I sent a few days ago I sent you a unique circle along with the hexagon and all the trig formulas, right? I think I did that before. even and odd identities. So sine of negative x is equal to negative sine x. Cosecant of negative x is negative cosecant x. Tangent of negative x is negative tangent of x. Cotangent of negative x is negative cotangent x. And then finally cosine of negative x is cosine of x. Secant of negative x is secant of x. So the only thing we need to know that is this function, this whole function is odd and cosine is even. Cosine and secant are even. The other four functions are odd. So even meaning cosine of negative and positive will be the same. Negative x or x still the same. The other odd function, they are the negative sign here. So cosine and secants are even, everything else is odd. And also if it is even, it is symmetric on the y-axis, and if it is odd, it is symmetric on the origin at the point 0, 0. Right. 2. Verify trigonometry. Identities. I brought up quite a few things here, but whether we actually do that, it's kind of difficult because each problem we might have to approach differently. So either we start with a complicated sign, and then transform to the similar one. To a more simple sign. Then convert both sides to equivalent expression. Or we might try to simplify the equation to something easier to prove. And the technique is even less helpful, even though we can write a lot of things like the simplifying and using algebra, but that kind of very general. So the technique here, that like I said, not particularly helpful. But one thing for sure, of course, we need to know all of this trig identities, and then there will be a lot more. Then we could use algebra or try to do. So like I said, lots of things can be done. So that's why I'm not even going to write out the tools that we need. After first few examples, then maybe you get the idea. Right. Now we'll try to prove this. Cosecant square minus 1 over cotangent is equal to cotangent of x. Right, so we try to prove this. By the way, before we do anything, I just want to note these important things. When we write, let's say, sine square, like that, what we mean is we have sine x and then squared. That's what we mean, and not that. This sine of x square and this sine x square. So whatever you do, this is incorrect. Sine square meaning sine of x square. Right. Right. So the proof here is we have cosecant. We start with more complicated side, so we start with the left hand side. Cosecant square minus 1 cotangent x. So that's what we have from the left hand side. Now let's go back to all of the trig identities. Just a second, let me find out what I sent you earlier. Oh, so I sent you that earlier, and of course this doesn't have any identities that we have today, so that doesn't help. Okay, so when we look at this, what can we use? What we see is the cosecant square is equal to cotangent square plus 1, because we see the cosecant square. So we will have cotangent square plus 1 is cosecant square. And we're going to use that and substitute into cosecant square. So we have cotangent square plus 1, and then subtract 1. One and 1 cancel out. We have cotangent square over cotangent x, and the square meaning the square on the outside. So we can cancel with one of them. And we just have cotangent of x. And that is equal to the right hand side. Right, so that is proof of an identity. That's what we use. Usually a more complicated sign to the similar sign. Right. Now, because that is one way to do it. The other way is a little more unorthodox, but certainly works, and less conventional. This certainly you can do. However, it's a little outside the box, but logically it works perfectly. Right. So, but before we do anything, try to simplify things, right? So tangent is like tangent over 1. And now let's cross multiply. By the way, this is not the proof at all. I might have to make some adjustment at the end. But first, let's cross multiply. Secant minus cosine times 1. And then sine times tangent. Right? So, if there's a fraction, cross multiply, eliminate fraction. Now, write everything in terms of sine, cosine. Secant is 1 over cosine. Secant is reciprocal cosine, and tangent is sine over cosine. Right. So we still have the denominator. I will multiply both sides by the common denominator of cosine of theta. Multiply both sides by cosine of theta. And then that cancel out. Cosine times cosine cancel out. We have 1 minus cosine times cosine is cosine square. That cancel out. We have sine square. Right? And then of course we can add cosine square on both sides. What we end up with is 1 equal to cosine square plus sine square. Right? That cancel out. Cosine square plus sine square. And because we know that this is true, because that is the Pythagorean identities. Right? So what did we do here? If there's fraction or ratio cross multiply or multiply by the common denominator, either way we're trying to eliminate all the denominator. Either cross multiply or multiply by the common denominator. And then at the end try to move things around. We can add something on both sides, and that's what we have. However, the most important here, if you do the proof like this, I'm sure there will be a lot of people will have a problem with it. because logically we start to prove this. Of course, when we start to prove that, we don't have it. So logically we cannot assume what we are trying to verify. So that logically doesn't work. However, we certainly we cannot assume that this is correct. So we cannot start from here and do all of this thing. However, what we can do is we can write this in reverse, and logically will work out just fine. So the actual proof is the reverse of what we just did. The actual proof we can write from the bottom to the top. The actual proof is the reverse process, meaning that we start with something we know and we start to end up with something we need to prove, and that logically works just fine. Like that, not the old school proof, but certainly works. So I just write all of this in reverse. 1 equal to cosine square plus sine square. Of course, that is Pythagorean identities. Nobody gonna have any problem with that. And then we can move the cosine on the other side. I'm just going to write this line, and of course to get from here to here we just subtract cosine square on both sides. Like that, we do everything in reverse, right? And then we're going to have this. Of course, on here we multiply and cosine both sides. On here we will divide cosine on both sides. We don't even need to write the step in green here. If we divide by cosine, 1 divided by cosine, cosine divided by cosine, and then sine square divided by cosine. So that's what we have. And then the next step is, of course, is that. And 1 over cosine is secant minus cosine and sine times tangent theta. And then the last step is secant minus cosine divided by sine equal to tangent. So meaning that we just divide by sine on both sides. So the proof, like I said, is not this process, it is the reverse of the process. And since this is true, the last one is true. And so that is the proof. So what we're trying to do is, if we write the expression, if there's any ratio, try to eliminate the ratio, and then write everything in sine, cosine, and try to eliminate that as well. And then we just write in reverse, and that will be a proof. Right. see cosecant equal to tangent secant minus cosine. Right? So just write that in reverse. That in reverse. Right, now, so like I said, if there's a fraction, trying to eliminate it. So I cross multiply in here. Cosecant times secant minus cosine and then tangent. So cross multiply, so there's no more fraction. Right, multiply it out. Cosecant times secant and cosecant times cosine and then tangent. Right, cross multiply, then multiply it out. Very normal thing to do. Right, now it could be very helpful to rewrite everything in sine cosine. It will be very easy to think after that. So cosecant is 1 over sine, secant is 1 over cosine, cosecant is 1 over sine, and then cosine. Tangent is sine over cosine. Right. So cross multiply to eliminate fraction, or multiply by a common denominator to eliminate fraction. So bottom line is, when we have a ratio or fraction, trying to eliminate that. Right, same thing here. So multiply by the common denominator of sine and cosine. Yeah, so I multiply every terms by that. I multiply straight across. We have that. And for each term, by term I mean the product's okay within the term, but not add or subtract. So now I multiply by sine cosine. Cosine and sine, I can put cosine on the top. And then multiply by the common denominator. And then the sine over cosine. Multiply by the common denominator. Right, multiply the least common denominator to everything, every term. Now try to cancel. Sine and sine cancel out, cosine cancel out. We have 1. Sine and sine cancel out. Cosine times cosine is cosine square. And cosine cancel square out. Sine times sine square. And then we just move the cosine square on the other side. As we have 1 equal to sine square plus cosine square. And of course that is the Pythagorean identity. So that's good. So what we do is, of course, that is not the proof. So we just say if we write this backwards, that will be a proof. Yeah. So if it is my lecture class, then I just say we're just going to do that instead of write everything backward. The reason we can do that is the process that we do, like cross multiply by least common denominator, do things equivalent relations. We can go from one side to the other without any problem. So the proof is just write this in reverse, and that will work. By the way, it's kind of difficult to ask you to prove on the test on my math lab, so we may probably don't have it. By the way, I post the review online on my math lab for the second test. So again, if there's fraction eliminated and eliminate fraction, there are two ways: cross multiply or multiply by the least common denominator. And when we eliminate all of the fraction, usually it ends up to something that is obviously true, something like that. And then we just write in reverse, meaning that if we have this going backward, we should have the beginning. Right. Now, try this. Cotangent. Cotangent is, by the way, there's no fraction here, so at least we don't have to cross multiply. However, cotangent, if we write in terms of cosine and sine, cotangent is cosine over sine. And that's a fourth, so that will be a fourth. And then cotangent square is cosine square, sine square. And then we have the other side. Cotangent square, once again, is cosine square, sine square. And cosecant square is 1 over, cosecant is 1 over sine, and that's a square, right? So once we eliminate all the fraction, trying to write that in terms of sine, cosine, right? When we do that, there are more fraction. And then from here I just say cosine square, sine square times sine square, sine to the fourth. Alright. Of course there might be a different way to do this, but that's what we have. Now, eliminate fraction, of course, multiply everything by the least common denominator of sine to the fourth x. sorry. Cosine square over sine square. Times the sine to the fourth x. And then cosine square sine to the fourth. Sine to the fourth. So cancel that. Plus cosine to the fourth plus cosine square this is a square, so when we cancel there will be a square left. And cancel out. Now put that. So of course, like I said, there's nothing wrong here, but we still need to have one more step. Right, notice that all of them have the cosine, all the terms have cosine, right? So we do one more step in here, divide everything by cosine square, because all the terms have the cosine square. So when we divide by cosine square everywhere, the fourth divided by the square, we have cosine square. Cosine square cancel out, equal to 1. And the proof, as always, just write that in reverse. And we have the proof. Right, so always eliminate fraction. So either cross multiply or multiply by the common denominator. So that's the first step. If there's some other function, it might be useful to rewrite as sine cosine. So only write everything in sine cosine, unless we don't have to deal with the rest. And then sometimes even when we have something that is common on both sides, just try to simplify it, and then we have it, and then write everything in reverse. We have the proof. E cosine of x over 1 plus sine x equal to 1 minus sine x cosine x. Right, so first there's a fraction, so cross multiply cosine times cosine is cosine square. Not just multiply, cross multiply. Cosine times cosine is cosine square. And then multiply them out. 1 times 1, 1 times sine x, negative sine x times 1, and sine x times sine x. Sine x and sine x cancel out. And more often than not, we end up with something that is trivially, that is obviously true, like the Pythagorean identity. And all we do is just write in reverse again. We're not going to do that here, but if we write that in reverse, we have the proof. Right, let's take 5-minute break here, then we continue at 2:05. Right, we continue. Prove that the following is not an identity. By the way, just want to show you something. If it is an identity, the graph will be identical, obviously. So let's just try to graph this one. Alpha y equal to, so I have a fraction, cosine of x, and then 1 plus sin x. Right, the other one, alpha y equal to, that's a fraction, 1 minus sin x, and then over cosine of x. Okay, before we graph, make sure that is in radian mode, and then let's see the graph. Right, and then you say, how do we know if they are identical? If they are identical, obviously they on the top of each other, and then we cannot see it. However, this is what we can do. You see, on this graph, when we have the equal sign, and between the difference between that symbol and that equal sign, and when we have this I call that a switch. Just switch is on, and the equal sign is off. So when it's on, like this, it will graph. And when it's equal, it's not, right? If we don't want to graph it, just turn that to equal sign. Sorry. Highlight it. Hit and enter. And now it turn to equal sign. The graph will not graph it. So if we want to graph it, have to be like a switch. Right. Now what we do is start that, go all the way to the left. Like that, and when we hit enter, we will change the pattern of the graph. Equal, set it above and below. What I do is I'm going to have this, meaning that it will see a little circle tracing along the graph. Now let's see this again. At first we will see the first graph, then we'll graph the first function, the left hand side. Now on the second function, we will see a little circle tracing along the first graph. So that shows that the graphs are identical. You see there's a little circle tracing along the first graph. Yeah, so with that we see, at least we can see somehow that they are identical. Of course, if you have the graphing calculator that have graphing in color, they graph a different color, and that's very easy to see. But that also works out just fine. Right. What we're trying to show here, that it is not an identity, so meaning that the graph will not be identical. In that case, let's just graph both of them. First we have sin x minus cosine x square. The other equation, sine square. So we actually have to enter sine of x and then square like that, minus cosine of x square, and then let's see the graph. So that is the graph of the first function. and then that is the graph of the second function. Of course, you see there's a way off. Right. Now, the difference between proving identity and disprove that it is not an identity or try to disprove it is a lot easier. When we disprove it, we just need to show that one point are not the same. So, for example, if we like in court, if you try to prove somebody actually commit a crime, you have to prove a lot of different things. But if you want to disprove it, you just show that there is an alibi, and that will disprove everything. So just like that, if we can show that at one point they are not the same, they cannot be the same, period. Right. So if we look at the graph here, look like when x equal to 0, the function are not the same. So let's say, let's try with that. So we see at x equal to 0, the left hand side equal to sine of 0 minus cosine of 0 and square. Right. We have a unit circle here. At 0, cosine is 1, sine 0. Right? So I have negative 1 square, which is 1. And then the right hand side is sine. We're going to put 0 for x. Right. Notice that this is sine of 0 square minus cosine of 0 square. Sine of 0 is 0, plus 1 square is minus 1. So we say the left hand side are not equal to the right hand side when x equal to 0. So the function are not identical. So to disprove it, just need to find one point that it doesn't work, and this is called a counter example. One counter example will disprove the identity. Right. Now with that, we go to the next section. Now the remaining of the chapter we'll go over a bunch of identities, so sum and difference identities is the first one. Right. Now, out of all of the identities that we learned in this chapter, this one is the most difficult to prove. because of that, if we have to memorize, if we have to choose something to memorize, these are the sum of difference identities are the only thing that I memorize. The other one, by the way, I highly recommend that you have this when you're taking the test. All the identities there, right? And with this identity we can prove the remaining one, right? So this we need to know, right? So cosine of a sum is going to be cosine minus sine and sine. And then cosine of a difference cosine plus right, and then sine of a sum sine cosine plus cosine and sine of a difference sine cosine minus cosine and sine. So before we go any further, note that for cosine, here we have the sign of plus and then minus, and this is this minus and plus. For the sign of a sum and difference, plus or minus, we stay plus or minus. So that's the first thing different between these two. For cosine, the sign in the middle will be different, will be opposite. For sine, the sign will be the same. So let's write a few notes here. For sine, the middle sign are the same. And for cosine, the middle signs are opposite. Yes, I forgot to switch to section 5.1 and now I have to switch to 5.2. Right. Thank you. I mean, this is fine. If you're watching it live, that is no problem at all. But it is only problem when it's watching the replay. But then again, you have a copy of the actual note, so hopefully you can follow. Right. But thanks. Okay, forget doing that. Right. For cosine, the middle sides are opposite. Right. So that's the first thing that we need to know. In the middle, cosine will be the same cosine is opposite and sine will be the same. Right. Now the second observation is this. For cosine, you see cosine, sine, so the function will be the same. Those two functions are the same, and these two are the same. And for sine, it's sine cosine and cosine sine, so there will be a mixture of sine cosine, or just say different. For sine, the function in the product are different. We have different function in each product. And for cosine, we have the same function. In each product. Right. So those are the difference between these two identities. Right. And the next one, I have no trick for it. Tangent of u plus v is tangent of u plus tangent of v over 1 minus tangent of u tangent of v. And then if there's tangent of u minus v, we just flip the plus and minus here. Tangent of u minus tangent of v, 1 plus tangent of u tangent of v. So, like I said, if we have to memorize some trig identities, this are worth memorizing, because the other identities we have the hexagon, and the rest of these identities, meaning the rest of this, we actually can prove them relatively easily, as long as we have these identities. So the proof for this is kind of difficult, but once we know that, pretty much we know the rest. Right. Now let's go to some examples. Now, try to prove my point. We prove a bunch of identities by just knowing this. The first one, prove cofunction identities. Cofunction identity is way back. It says that we go from by the way, the first one we will prove is of pi over 2 minus x is equal to cosine of x. So co-function identity is this. We will go from a function let's say x. We can go from that to a co-function. If we have a function equal to a co-function, then x plus y have to be equal to pi over 2, meaning they are complement to each other. So we go from a function to a co-function like sine, cosine here. They have to add up to pi over 2, or it could be multiple of 2k pi, meaning either pi over 2 or any coterminals angle of pi over 2. So if this is true, then we have that, and if we have that, the other one is true. So those two are if and only if statement. That is if and only if. So that is the co-function identities. Right, now we'll try to prove it. So I will start with this left hand side here. Right, now for sign of a difference, what I have is, for sine, the middle sides are the same and the function are different. So from here, what can I say is the function is going to be different sine and cosine and sine. So the sign of a difference, the function, like that. Next, the sign in the middle for sine is going to be the same. So that minus, we're going to have minus. And then we just have two angles, pi over 2 and x. Pi over 2 and x. Right, so just that. Sine of pi over 2, sine of 90 degrees is 1, and cosine of pi over 2, cosine 90 degrees is 0. So I have 1 times cosine and 0 times sine. And that gives us just cosine of x, which is the right hand side. So it's simple enough. Two. Try to prove this. So let's start with the left hand side. Right. Now tangent about difference, we're going to use this formula here. It's going to be tangent of x. Tangent of pi over 2 minus tangent of x over 1 plus tangent of pi over 2 and tangent of x. I'm just applying that formula. Right, now we're trying to find the values. Tangent of pi over 2. What is that? Tangent of 90 degrees. Or if we have in the radian mode, tangent of pi over 2. Oh, it's undefined. Doesn't mean that they are not equal. It just means that whatever we use in here doesn't work. So if it doesn't work, try something else. Right. Now try something else. Now, what can we try is that tangent is sine over cosine. So I'm going to write sine over cosine. Now, sine, the function will be different. Sine, cosine, minus cosine, and sine. In the middle is minus. It will be the same. Right, and then the angles. Pi over 2, x, pi over 2, x. And then for cosine, the function will be the same. And then the angles. The side in the middle are opposite. Right, so we have that. Next, sine pi over 2, sine 90 degrees is 1, cosine 90 degrees is 0. Once we put those values in and we simplify, we will have cosine on the top times 1 times 0 cancel out, times 0 cancel out, and then just cosine over sine, which is tangent cotangent of x, which is equal to the right hand side. So we cannot prove it using the identity directly. We have to switch around using the sine cosine, and it will work after that. Right. So normally we can prove the identities. We can do a lot of things. B. Find the exact values of exact, meaning that we're not going to use the calculator and get a decimal number. Sine of 75 degrees. Right. Now, before we do that, let's go to the unit circle. Right. So on the unit circle, we have the special values of pi over 6, pi over 4, and pi over 3, or 30, 45, and 60. Or if back in the day, what we used was, remember the hand trick, those are the special values. Those are the values that we know. Suddenly 75 is not one of them. So however, here what we can do, we can split the 75 in any combination of 30 and 45 or 60, and the first one come to mind is not 75 degrees. We can say, how about 30 plus 45? Because 30 plus 45 is 75, and then we use the sum, the sign of a sum. Sine is sine, cosine, and cosine, and sine. So sine of 30 degrees, cosine 45 degrees. In the middle, the sign will be the same. If that's plus, we're going to have the plus, but the function will be different. Sorry. Sine of 30, right? 30 degrees is here. Sine is the y value, so the second one is 1/2. Cosine 45 degrees. 45 degrees here, and cosine is the first values, square root of 2/2. Right. Of course, we use that unit circle, or we're going to use the right hand trick. Cosine of 30 degrees. So we're going to cover 30 degrees, and cosine is the number of fingers on the left hand side, on the left side. Square root of that divided by 2. So square root of 3 divided by 2. And sine of 45 degrees. And we have 2 fingers on the right. For sine is on the right, cosine is on the left. Sine, so we have 2 fingers. So we have 2/2. Either way, we use the unit circle on the right hand trick. Right. Multiply across, we have square root of 2 on the top over 2 plus square root of 6 over, 2 times 2 is 4. And then the common denominator is 4. Common denominators are 4, and then we just have square root of 2 plus square root of 6. So simple enough. How about cosine of 105? So trying to get a combination that gives us 105. There's a few things we can try. So it's cosine, and to get 105, let's say 30 and 75. That doesn't help, even though we know 75. 45 and 60, that certainly works, right? 45 and 60, or could be 135 minus 30. But here, let's see 60 and 45. Of course, or we can use 135 minus 30, or a bunch of different combination, because 135 on the unit circle, we have the values, we have the exact values. Alright, now cosine of that, cosine, the function will be the same. 60, 45, 60, 45. But in the middle, the sign will be opposite. Alright, now we find the values. Cosine of 60 degree. Either we used the unit circle or the hand trick. 60 degree, one finger is on the left, square root of 1 over 2. Cosine 45 degrees, on the left there are 2 fingers, so square root of 2 over 2. Or we could use the unit circle. Sine of 60 degrees, 60 degree, sine is the y values. So 60 degree, sine is the y values, square root of 3 over 2. And sine of 45 degrees, sine is the y values, square root of 2 over 2. And when we multiply square root of 2 over 4 minus square root of 6 over 4, so square root of 2 minus square root of 6. Alright, try something else. How about something in radian? Let's see something. We haven't used tangent yet. So tangent of pi over 12. Right. So pi over 12. Kind of difficult to work in this in a fraction, but so what, it will be easier if we just convert the pi over 12 into the degrees, into degree mode, into degrees measure. So to get to degree, we're going to put degree on top, then pi at the bottom, so that the pi will cancel out. 180 divided by 12 is 15 degrees. Right? $180. Right. 15 degrees. How do we get to 15 degrees? The combination of 30, 45, and 60. So that's very simple. 45 minus 30, or 60 minus 45, or a lot more different combination. But it will be tangent of, let's do 45 degrees minus 30 degrees. So sine of a difference. Oh, here. We read the formula over there. So it's going to be tangent of 45 degrees minus tangent of 30 degrees over 1 plus tangent of 45 degrees tangent of 30 degrees right, tangent of 45 degrees. For tangent, we can use the unit circle and then let sine over cosine is tangent, or I'll use the hand trick. Tangent of 45 degrees, we write 45 degrees. and then the tangent is square root of the number of fingers on the right divided by square root of the fingers on the left. So there's 2 on the right and 2 on the left. So it might be silly, but we can just say square root 2 over square root of 2, which is of course 1. Tangent of 30 degrees, square root of the fingers on the right over square root of the fingers on the left. So that, and then 1 plus tangent 45, square root 2 over 2 is 1, tangent 30, 1 over square root of 3. So we have 1 minus 1 over square root of 3 over 1 plus 1 over square root of 3. Of course, that is the exact values. It's good already. However, it doesn't look very nice when we write like this. So let's just multiply by the denominator of square root of 3, top and bottom. Square root 3 times 1, square root 3 and square root 3 cancel out. We have that. Square root 3 times 1, square root 3 cancel out. So we just that's what we have. Right. So the sum and difference, the application is very simple. Let's go to something a little more complicated. Let's sine of u equal to negative 3/5 and u is in quadrant 3. And we have cosine of v 12/13 and v is in quadrant 4. Now we need to find sine of u plus v. Right. So first, let's start with sine of u plus v. For sine, the function would be opposite. The function would be different. Sine, cosine, cosine, and sine. The angle u, v, u, v. The functions are different, but the sign in the middle are the same. If it's plus, it will be plus. Right. Now just put all the values we know. What do we know? Cosine of v. Cosine of v. And sine of u. Sine of u is negative 3/5. Cosine of v, we do know that as well, is 12/3. Cosine of u, don't know that. And sine of v, don't know that either. Meaning that we have to find those two first. While we know it, put it back in here. Alright, first, trying to find cosine of u. in that case, we write out the information for u. Sine of u is equal to negative 3 over 5 in quadrant 3. Right, so we draw a triangle. Sine of u is negative 3 over 5. The ratio for sine is opposite over hypotenuse. Or we can use x, y, and r. If we use x, y, and r, then it's going to be y over r. Right. Regardless, I'm going to draw a triangle. The angle is u. Opposite over hypotenuse, or r. So from here, r cannot be negative, so we say r is equal to 5. So hypotenuse is equal to 5. And then opposite has to be negative 3, so y equal to negative 3. We just need to find x. Right. So we have the Pythagorean identities. X squared plus y squared equal to r squared. X squared plus y squared we know is negative 3 square, and r square is 5 square. So x squared plus 9 equal to 25, minus 9 on both sides, x squared is equal to 16. Take the square root on both sides, x equal to plus or minus square root of 16, which is plus or minus 4. Right, next, this is in quadrant 3. If it is in the quadrant 3, x is negative, so we will stick with the negative sign. And finally, we go back to cosine. Cosine is x over r. X over r. Right. So cosine is negative 4/5. Cosine of u is negative 4/5. Next, we're going to find sine of v. And we use the information given for v, knowing that we have sine of, cosine of v is 12 over 13, and v is in quadrant 4. Right, so cosine of v is 12 over 13. Cosine is adjacent over hypotenuse, or x over r. So we have a triangle. The angle is v. X, or adjacent, is 12. Hypotenuse, or r, is 13. From this we can find y easily. So we have x squared plus y squared equal to r squared. X squared is 12 squared, and y squared we don't know. and r square 13 square. Right. And then so we solve for y square is 13 square minus 12 square. Should be 25. And then we solve for y, which is plus or minus square root of 25, or equal to plus or minus 5. Next, this is in quadrant 4. In quadrant 4, y is negative. So we again stick with the negative sign. So cosine is given, we can find sine, which is y over r, negative square root of 5, negative 5 over 13. Right, and finally we can go back to that. Sine of u plus v equals sine u cosine v plus cosine u sine v. Sine of u negative 3/5, cosine of v 12/13, cosine of u negative 4/5, and sine of v negative 5 over 13. Right, so all the values we have, find 5 cancel out, minus and minus after plus, so we will have multiply across negative 36 over 65 and then plus 20, sorry, the 5 cancel out, right? Oh no, just multiply across, doesn't matter. 20 over 65. So that's negative 16 over 65. Yeah, even though we can cancel, but I'm just going to keep it like that so we can do the common denominator easier. Right. Right. So that looks like what we have. Right, so it's not that bad. The backbone of this, of course, is that formula. We don't know that. Finding this, of course, there are a lot of different ways to do it, but let's go way back to chapter 2 when we can do this easily. Right, so this is about 3 o'clock, so I'm going to stop here. By the way, as mentioned before, I posted the test 2 review already. After we finish everything on Thursday, I will post test 2. And then we only have a couple weeks left after that. Since the classes are designed to, instead of perhaps 6 hours a week, we only have 4 hours a week. So the time that we do here will not be enough to cover everything I wanted to cover. So because of that, I'm going to have some offline lesson offline video that I recorded earlier. One of those is on my YouTube channel already. That is for chapter 7. The reason I choose chapter 7 because it kind of what we use on chapter 7, we do not rely too much on the other chapters. So that's why I want to do that on the offline video. There will be 3 tests. 3 tests and a final exam. and the final exam will be on the last day of class. By the way, I will talk about the final. The final exam is not on my math lab. The final exam is on Blackboard or eCampus or multiple choice. But the way you take it, remember at the beginning of the class I sent out a survey and asking if you have a webcam or not. On the final we're going to need a webcam. However, if you don't have the webcam for the final, there's some other thing we can do. I'll let you know. I will send out an email and a video explaining what we're going to do on the final exam. But other than that, do you have any other question before I end the stream? Just one comment in general. The final looks like it's going to be on the 14th of May. So like I said, we have like 2-3 weeks left. So make sure that you catch up with the homework and catch up with the test. I don't want you to do everything at the last minute. Oh, it is not a stream, it is a link for the video. It is there already. The link is, I mean the video is there already, but I did not send the link yet. So it is also a video like this, but it is not recorded live. That's all. And that's for chapter 7. And then if we are behind, I will have to do another video for that. But like I said, it will be there. I will send you the link. And the chapter 7 kind of stand out of completely different things. So in that case, you can just go ahead and do the homework. I'm going to post the homework for chapter 7 as well. So we're just going to need to do that. It doesn't rely on the other chapters. So we should be fine. Great. Once again, do you have any other question before I end the stream?